Okay, hi again. I guess it's been a while since we. So today we're going to look at the really cute hashing-based data structure. It's going to call Invertible Bloom Lookup Tables, or IBLT, Invertible Bloom Lookup Table, IBLT. I guess the name here is inspired by a classic data structure called the Bloom table. There's some similarities between the two, but they're really also quite different. So this data structure here is due to Goodrich, Mitzenmacher. So what does it do? So I think I'll try to motivate it first with two different types of applications. So the first one is, let's say that you maybe you have some web server or some other service, and in this service you can have users log in and they can leave again. So users log in and they leave. Later. And so for these users, maybe you want to store a lot of auxiliary data for each of the users, and maybe you can use this data to do statistics. So let's say there's some auxiliary data. But this data might be kind of nice to have. It's not critical for your application. It's nice to have, but let's say that you suddenly have a lot of traffic, a lot of users logging in, then perhaps you're okay with temporarily not having this data available. Makes sense? So you can kind of say, okay, if I suddenly have a ton of users, maybe my memory, I don't have enough memory to store all this auxiliary data for all the active users. So I just kind of temporarily say, I don't have this data available. Maybe I reduce the amount of services I have available. But as soon as the number of users that is currently online drops below some threshold, it starts working again. Okay, so that's kind of the idea in this data structure. So let's put it here. So there's a threshold. Threshold T. The idea is that whenever there is at most T items or users or whatever present, everything should work fine. But if we temporarily have more than T active users, whatever data it is, it will just not function for a while until it drops below this threshold again. So maybe let's make it a little bit more formal. So what we're storing in this data structure is key value pairs. We store key value pairs. So we can insert a new pair, delete a pair, and we can query, given a key, what is the value that is associated. That's similar to maybe these users log in. When a user logs in, the key is maybe the IP address of whatever of this user. Then there's some associated auxiliary data in the value. You can insert these key value pairs. And when a user leaves, again, you delete the key value pair corresponding to that user. And so basically we have a couple of operations. We have an insert. Let's say key K and V, a key and a value. We have a delete key value. Then we have a get operation. Takes the key and returns the associated value. And we have one more operation here for list entries, which just outputs all the key value pairs that are in the database, the data structure. And then the special thing is it has this threshold, and then kind of like the interesting property is that operations work. While then yes, data structure and store it. Okay. So somehow you can insert more. Of course, an obvious way is just, okay, let me just store a hash table, and when I exceed the threshold, I just say, oh, it doesn't work anymore. But the interesting thing with this data structure is that you can kind of keep inserting pairs, and you don't know which ones will disappear eventually, which one will be deleted first. Just as soon as enough have been deleted, and you go below the threshold again, and start working once more. So this seems difficult to achieve with a normal hash table, right? So let's say a lot of key value pairs arrive. Maybe we can have an example here. Let's say I have a threshold of 2. And then you see, okay, maybe someone with 1 at value 3 arrives, 3, value 2, 2, value 10. So if you kind of see, this is an insertion of this pair. To begin with, you're fine, right? You're not above the threshold. But now you come to the third key value pair. And what do you do if you're kind of constrained to not using more memory than this threshold, right? So your memory usage will always be proportional to this threshold here. So that's the kind of interesting property, like the memory here. Memory proportional to t. Doesn't depend on n, but on t. So if you see this insertion, maybe there are more here, 5, 7, so on. As soon as you go above the threshold, you don't know which one will be deleted first, right? So it's really hard with the classic hash table to say, oh, I'm just gonna store these ones and forget about all the rest of them, right? So this data structure really supports, I don't know which ones are gonna be the last ones remaining. So all these are insertions. Third. And then maybe I have a deletion now of 1,3. I have a deletion of 5,7. So on, right? But I don't know at this time that the one that's going to be left is the 3-2 pair and the 2-10 pair. Okay. So this invertible Bloom lookup table supports all of these operations, insertions, deletions, get operations, this entries operations, without knowing which ones will be executed, which ones will be left. So I can do a lot of insertions, way more than T insertions, and then afterwards I can delete a bunch of the key value pairs, and it'll just start working again as soon as the number of key value pairs drops below this threshold. So it's a little magic that this is possible, but we'll see how to do it with randomization today. And that's one kind of application. You can kind of, okay, I have a memory budget that I cannot exceed. I want to store auxiliary data, and maybe I can just reduce the services I have available if there's just too many at some given time, too many key value pairs present. My memory budget will never be bigger. Let me give you one more kind of motivation where something like this could be useful, that you can kind of say that I could temporarily have too many items in my data structure. So this is another example here. So let's say you're storing a database, just a key value pair database. Key value database. So I guess a common technique if you want to scale the database and you want to have fast insertions and deletions on such a database is to use to replicate the database. Right? So you can have multiple copies of the database. Maybe there's a copy A and a copy B. And if you want insertions and deletions, I guess there's several ways you can approach it. Right? If you want, if you're okay with a slow insertion time, you can kind of wait for all of the database. I want to do this insertion, then I wait for all the databases to say, okay, I've implemented this insertion, right? So they all kind of block until they all implemented it. You could also say instead that, okay, I allow some small difference between these two databases, but I just want to make sure that they're synchronized every now and then, like say maybe once every minute, they should be synchronized or something like this. So let's say we're in this latter case that these two servers, they store some set of key value pairs. They're not exactly the same, but they're very close to being the same. So maybe we can say there's a set of key value pairs in SA, there's a set SB, and SA is roughly SB. These two sets. And now let's say I want to synchronize these two databases. What could I do? So Because if I'm not keeping track of the changes since last time or whatever, one thing I basically, the simplest thing seems to be just send my entire set to the other server. I just send the database, basically all the key value pairs, and then the other database can kind of synchronize, add once it's missing, and then maybe you can send your database back, and also to give the set of key value pairs. Okay. We're going to do something, but this is going to use communication proportional to the size of the database. Ideally, you'd like to only send a message with a length proportional to how different the two sets are. Right? That would be ideal, right? If you could get what we really want is a message length proportional to, it would say, the size of SA with the keys that are in this first set that's not in the second set, and vice versa. So this is called the symmetric difference of the two sets, right? Those that are in only one of the sets. We'd like the message length to synchronize these two databases. It would be cool if you could send a message that's only this long. Right? I just have two sets. So how could I do this? The really cool thing is I could do it using one of these invertible Bloom lookup tables. So let's say I'm also storing my set in an invertible Bloom lookup table with a particular threshold of t. Let's say I know, maybe I know that this symmetric difference here is not too large. Let's say to start to begin with, let's say that there's about t items symmetric. What could I do if I have this invertible Bloom lookup table with a threshold of t? I guess I could store my entire set SA in such an invertible Bloom lookup table, right? So I just insert it into the database or the data structure. The memory usage of this data structure is proportional to this t. So I insert a lot of keys, and this is much bigger than t. I send the memory footprint, if you will, on this data structure to the other server. What does the other server do? The other server goes through the entire set B and runs a delete operation for all the keys in set B. Right, so here you insert all the keys in the set SA. Now you delete all the keys in the set SB. The ones that are left are the ones that were inserted here, but not deleted there, which is the set of keys in A that are not in B. And similarly, B could insert all the keys in SB, send it to A, and A could delete all the keys in SA. And the nice thing is that if the only ones that are left right is this symmetric difference. And if this is below the threshold, number of key value pairs have dropped below this threshold T, and the data structure starts working again, so you can kind of extract all the elements of the difference using this list entries operation. Right? So it's kind of a cool way of saying I have two sets. I just know that they're very close to each other, that they're almost the same, but I don't know how they differ. Then I could just insert all my key value pairs in the lookup table, send it, and delete all the keys in my set. And then I run the list entries afterwards and recover all of it. This is a pretty cool trick. So of course the surprising thing is that perhaps this is possible. How can one use it? We're going to start by analyzing a slightly simpler version of it, a version in which you never delete anything that wasn't inserted. So this is a little bit easier to handle. I only delete stuff that has actually been inserted, which may be similar to the clients logging in and then logging out again. Right? In this case, you always have an insertion followed by delete. This is fine. For this case over here, you do have a problem if there's something in SB that is not in SA, because then you're deleting something that wasn't inserted. We'll see later how to handle that as well. But first of all, let's try to see how could such a data structure look like when you only delete stuff that was actually inserted. down. We have those operations, insertions, deletions, and just list all the entries in the data structure. So it's quite simple, and it looks like many of the other data structures we've seen in the slides. What is the IVLT? So it has two parameters that we're going to choose. One of them is K, and the other one, what should we call it? Let's not give it a name. Let's say the other one just depends on T. So what we have is basically have a matrix or a table with K rows. Let's say K is at least 3. And then we have some columns. The number of columns depend on the threshold. So for now, let us say that we have 2 T columns. Twice the threshold. So this is we have this table, and yes, similar to all these count sketches, so we have a hash function for each row of the table. And I guess in this first analysis that we're going to see now, they're just universal. So this is we're going to analyze this get operation first. And for that, they're just universal hash functions. That's sufficient. We'll see later for this list entries operation that we're also going to handle. We will make them, we'll need true randomness to go through that analysis. Now they're just universal. So what is stored in the entries? So if we look at one of those, let's call it a cell. In this first solution where we're only deleting stuff that was actually inserted, this cell has, I guess, 3 variables, if you will. So one of them is a count. One of them is a key sum. And one of them is a value sum. So with these, how do we insert and delete? So it's quite simple. So let's say we're inserting a key value pair KV. So then we say, go. Now this case is called the same as FK. That's unfortunate. Want to call it something else? Let's say the key here is called, I don't know. It's also saying, let's call it X. So we're gonna go through all the rows. We're gonna get this cell in row I. Use the I hash function on X. We always do. And then what do? We just increment the count by 1 in the cell. And so basically the count is keeping track of how many elements hashed to this entry. And I guess we're not going to plus equals X. Key sum, we just add the key to the key sum. Add the value to the values. Okay. So this is that's the entire insert operation. So basically, you just hash it in every row, and in that cell that it ends up in, we're saying now there's one more item that hashed here. Key sum is incremented by the key, and the value sum is incremented by the value. Very simple. And what does the delete do? What do you think it does? Anyone? Any guesses? What would be the natural thing to undo this change we made here? Yeah. It's the opposite of increment the count of something. Yes. Yes. Exactly. Maybe then let me just say minus. Thanks. 15 minutes. So super simple operations. So I guess the question is, how are we going to answer this get operation? And I guess it gets way more interesting when we get to this entry operation. These are the simplest parts. So now we have this get operation where the argument is we basically get a key as argument. We have to return the associated value. If the item is not there, I guess we have to say it's not there. It was not inserted. And then we have this special, because we have this threshold, right? Sometimes we might have a lot of keys present in the data structure, and maybe we're not able to answer the query. So we're also allowed to say, I don't know. Right? But we like it to be the case that when the number of keys is below the threshold, it's quite unlikely that we say, I don't know. So, okay, so maybe this is an exercise. Think for a minute or two, maybe discuss with the one next to you, what would be a reasonable way to try and implement the get operation?
Ja, så kan vi udvikle det bare og returnere hvad vi we don't know. If only there's zero, then I guess. Or if you don't live with zero, yeah. Zero. Yeah.
Okay, any suggestions? Let's have to start. Yeah.
As long as we're below the threshold, probability. So, if we check for each row, if the count is 1, then we'll check if the keys are values. Otherwise, it's in the next.
Yeah, so we go here, so we say if, let's say C again is k index I hash I of x, and you say if C dot count is 1, and what do we do here? You said?
Then check if the keys are up.
Yeah. If let's C dot key sum, and what we do in this case?
Checking the values.
Yeah. Yeah. What if it's not?
Then it does not exist.
Yeah. Not there. Yeah. That's right. What happens if we And then what happens if we complete the loop? Yeah, we don't know. Is there anything more we can add to this? Makes it work even better. The one more, yeah.
Is see that count is 0, then we know it's not there.
Yes. Yeah, so this, I guess, is the solution, right? So you go over all the rows of your table, you hash to whatever entry x supposed to being stored in. You check if the count is 1. No, is there only one item stored here? If there is, you know that the key sum is just that key. So you check whether the key sum equals 3. If you go query key x, and if it does, you know also the value sum is just the sum of a single value. So you can just return it. And otherwise, you know that it's someone else hashed here. You are supposed to hash here if you were present. So you can conclude that you were not inserted, and it's not there. Yeah. And finally, if the count is 0, we can also conclude that you have not been inserted, otherwise you would have been in this position. And then finally, if we loop through all k rows and we don't find it, and none of these things happen, then we basically give up and say, I don't know. Right. So I guess the interesting thing to try and analyze now is what is the probability of don't know when the number of p-value pairs n is at most the threshold. Let's look at this case. But we're not going to give any guarantees when you're above the threshold. In that case, we're probably just going to say, I don't know most of the time. That's kind of the nice, graceful way of saying, I don't know. It's too full. So we want to kind of bound the probability of don't know. Okay. So how would we go about analyzing the probability of saying, I don't know? So what about, maybe to begin with, what if case 1, how would we analyze? If there's just one row. What could we try and do? So is this something that has to happen for us to say don't know? Being bad in some sense. Yeah, there has to be a hash collision, right? Between your query key x and someone who's not equal to x, right? Some other key that was inserted. So let's say the keys that have been inserted are called x1 to xn. And there has to be collision between your query x and some xi that is not equal to x. If x is among them, it of course collides with itself, but that's still fine. You can still answer it here. The only thing that can go wrong is really that there has to be someone else that you collide with. You could even say that if x is not among your keys, you actually have to collide with 2 others, right? Which only gives better guarantees. But let's just look at kind of the weakest guarantee we can get. So basically, we want to say, okay, the probability I don't know when case 1 is, maybe let's define an event. EI is the event that hash. Maybe let's call it ij. So let's say the j hash function applied to x is equal to the j hash function applied to xi. And we're only looking at these events for xi not equal to x. So then what we have here, right, is if we just look at the simple case, then we have the probability that there exists, what do we say, this is the union over I equals 1 to n. Maybe let's say, let's do union over those i's such that xi is not equal to x. Let's just put 1 here. This makes sense. This is the event that we care about. This event saying the union over all elements that are not equal to x, of having a collision between x and xi. This is really like this is the range we care about, right? This is saying at least one other item is colliding with us when we use our hash functions in the first row. Okay. So how can we bound this probability of this union? Yeah.
Union bound?
Union bound, right? So it's at most so we use the union bound. So it's at most the sum for those i's such that xi is not equal to x, and then the probability. Okay, and what about this probability? What can we say about this probability? The probability of colliding with xi, when x and xi are different.
Yeah, it was universal. We know that it's 1/2. No, n.
1/, yeah, the number of buckets, and the number of buckets was 2t. So yes, we can just use universality, and I guess we wrote that somewhere. API is universal. So which again, if you remember, right, this is this property that the collision probability is at most 1 over the number of output values. This is universal APIs. So now it's the sum over those i's where xi not equal to x of 1/2t. There's at most n items in the data structure at this time, so this is at most n/2t, and this is at most. So the probability that I collide with someone in the first row is at most a half. What about larger number of rows? Like, what is the chance that we cannot answer the query if I have k of these rows? What can we say here? For general k, what can we say about it? Yeah.
So if we assume that the hash functions are dependent just by
Exactly. If we use independent random seed for our hash functions, then the probability of failure, basically they all have to, like need to have a collision in all of the k rows. So I guess this is how do we write it? The probability of, let's write it as the intersection j equals 1 to k of the union. The formal way of writing it, e I j. I guess it's less than equal to product over all of them, and then this probability of a half, right? So for general k, if we have k rows, the failure probability is to the minus k. So I guess in many of the previous lectures we've called the failure probability delta, and then I guess you can see, like before, if you want to express k as a function of this delta, I guess it would be log base 2 of 1 over delta for failure probability delta. Right. So this is fairly simple, and it gives us this get operation with a failure probability of 2 to the minus k. Oh, how are we doing in time? Yeah, let's start motivating the next part, this list entries operation. This is, I guess, the most interesting one. All of this is very straightforward. Looks a lot like stuff we've seen for hash min, the count min sketch, or what have you. The list entries is when it gets really interesting. So let's have a look at list entries, right? So list entries is supposed to output all the key value pairs that are being stored in the data structure. I think I want to use them. So now we want to output all the entries, right? All the key value pairs. Of course, the naive thing would be, okay, I could choose a k so that this failure probability is like super small, like 1 over n or something like that, or maybe even less. And maybe I just query for all the possible key value pairs. It sounds very inefficient. I just try and do this. We're going to try and do something more clever. Okay, what would be, so let's say, so this is your data structure, right? This has these counts, key sums, and value sums. If I wanted to extract all the key value pairs in this data structure, what would look like a natural strategy? You don't have to analyze it, but what seems like a good idea? Anyone have any? Yeah.
We go through each cell, and then each cell where the count is 1.
Yeah.
And then I know one key value pair.
Yeah.
And then I remove all of those and then do it again until it's empty.
Exactly.
Or until I don't have to and don't.
Yes. Exactly. So I guess in pseudo case, pseudocode would write something like while exist C. So let's say this is a cell such that C.count is 1. Let's I output whatever this means, add to an output list, C.keysum, value sum. Then I run delete C.keysum, value sum. It makes sense. It's a very natural strategy to just keep looking for cells with a count of 1, and then when I start deleting these other ones, that's going to help me in finding more places where the count is 1, right? Because they're colliding with each other, and now we're deleting them, and hopefully things get even better. Okay. So I think after the break, we'll analyze it. I think before the break, let's try and see if we can actually implement this really efficiently when we're below the threshold. So when we again have this n less than or equal to t, I want to claim that you can actually implement it in time proportional to the size of this table, so an O of kt time. So that's a simple data structure exercise, maybe. And maybe spend 2 minutes thinking about how can I implement, because this check here, why there exists a C with a count of 1, right? That is, you could do it by looping over the whole table, but then you would have to do that for every key value pair you output, and the runtime would be a little bit slow. I guess would be, the size of the table times n. So it'll be kind of slow. You can actually get it much faster. Try to think, how could you implement this loop, get a faster runtime? Just think for a minute.
No, yes.
Okay, let's see. Any good suggestions? I think it's pretty nice exercise in classic algorithms. Maybe it's almost one of these programming competition type exercises. So, yeah, any ideas how to do this?
Each time you delete, you check the cells that you have deleted from, and then you also got the one that you delete. Use that to output. So you only need to look through all the cells once, and you know that the ones before would have been deleted more.
Yes, that's basically the idea. Yes, I'll try to formalize it in a way. I think one has to be kind of careful to make absolutely sure that you get the right thing. But I think one way to do it is basically what you're saying, right? So you loop through. I think I'm going to use a queue that it's an empty queue to begin with, like a queue data, so you can push it up from this queue. And then I think I would go over all the rows, go over all the columns. And then I want to say, here I'm going to say if your count 1, and I think I want to add it to the queue. Good. Some value sum like this. So this is kind of just to begin with, and then I think I'm gonna do afterwards. I'm gonna say while queue non-empty. Let's write it like this. While there's still key value pairs, I think I want to drag the key value pair. Let's call it xv. Dot pop. And I think to be careful with not deleting and deleting again when you have a non-constant k, I think I want to check here. I want to loop over all the rows again here, so we have to delete it. One, so we have enough space here. So I'm going to go over all the rows, and then I want to check if space. Okay, I dash I dash it's plus see that count. I think actually if I see one that's 0, I think technically I have to break. Let's just go in here. I guess we have to delete it from this one. Times some x value sum times the value. Now I need more space. Let's continue. Well. Okay, so I go over the rows, I delete it, and I guess we have to check if it drops to 1. This is just in the continuation of this. Then we check if c.count is 1. Then we will add it to the queue. Good. Value sum. This. Good. This will definitely extract everything. I'm a little bit in doubt whether we'll actually get the fastest runtime now. Yeah, so we need to do another check or something like to make sure that we're not putting the same key in multiple times. Yeah.
Yeah, exactly. But I think you have a problem with the queue. I think you need to change it to a list and an index, because if you pop your index and you then somewhere in your delete get a new count 0, you put it in and you have already pushed the pop so that you can know.
Yeah, we only want to put it in once, right? Every key. So maybe we could, we'll start a hash table and check. This is one way. And let's say hash, call it that. That's a set of all the keys that have already been extracted. Not contains. Let's write it like this. Maybe there are prettier ways of doing it, but this will be sum. Then we do this, and then we do h dot put key sum. Then probably we should also do it here. I guess also when we pop it here, we should add it to the output. This probably does. Let's see. Yeah,
Doesn't work.
doesn't work. What do we miss?
At count equals 1 should also check if that contains.
If the count is 1 here, you say we should not.
You should also check
Yeah,
that.
we should also check. Yeah, I guess we could get a too large runtime if we could. Yes.
No, it just doesn't.
It just doesn't work.
You can output, you put the same key value in the same
Twice,
yeah, and then you put it twice. And then if there's one of these entries which has 2 already, then you
Yeah, we delete it twice. Yes, you're right. You'll only put it if it's not already there. Yes. Say and dot h contains. What did I call it? I called h not contains. Wait, not contains. I didn't see that one. So. Okay. Now I think we got it right. So we're only going to insert it the first time we see it. We're checking whenever we're going to insert it and popping it. We're deleting it from all the rows, checking every time we look at a cell whether its count drops to 1 and whether we have not already seen a count of 1 for this particular key. In that case, we're going to push it to the queue to be later extracted, and we're going to remember we only did it once. So then I guess we can try and analyze the runtime. Of course, this loop only goes over every entry of the table once, and it's constant time per entry with a hash table with expected constant time. So that's order tk for this first loop. And then I guess the observation is that any key is only extracted once because we do these checks with the hash table. So the number of times that we execute this loop is at most n. Whenever we do it, we have a loop here over k rows, where we do a constant time operation in each. So that's at most nk, and n is at most t, so t time. So we can do it in linear time in the size of the days. Right. Good. But one has to be very careful, yes, to not mess this up. You have to do these checks. But I think this implementation that we have now is okay. I think this is a good time for a break before we start analyzing what is the success probability of this procedure.